So I'm a developer advocate. I had a really nice long introduction by Mary. Thank you. So I'll just kind of shorten it a little bit. I'm a developer advocate, have been for the last few years at Neo4j. I like learning technology, and then I like sharing what I've learned in a variety of different ways. That includes meetups, conferences, virtual events, so on. Somewhat recently, I have also now a tech blog and a tech podcast that I really enjoyed working on and doing content for. I do have a few other hobbies outside of technology and work, but most of those boil down to the fact that I'm kind of a geek in a variety of different ways, and I kind of enjoy that. But if you think of questions outside this event, past tonight, weeks, months down the road, feel free to reach out to me. My contact information is here, and it'll also be on the last slide too, but I'm happy to continue the conversation or talk data, tech, Neo4j, so on. Okay, so we hear a lot of terminology slung at us, especially with this new kind of AI era, and any new era that kind of pops in, you have new terms popping up. But this one I have felt, especially as a developer trained, not mathematically trained or data science trained, as a developer training, a lot of these terms were very unfamiliar and just almost felt overwhelming. So we're going to try to just start from the ground and build up relatively quickly, but give you a good foundation of the intro concepts, and then show you how it actually works when you build something with it. So starting very basic, just the definition of generative artificial intelligence, which I pulled from Wikipedia. Artificial intelligence capable of generating text, images, or other data with generative models. So it produces an output, often in response to input, takes input, produces output. Typical computer system. Generative AI models learn the patterns and structure of their input training data and then generate new data with similar characteristics. So it's going to take an input, it's going to find something similar that it has in its trained data set, and it's going to try to produce something new, but that's similar to that. This is where we get large language models. LLMs are pretty cool. They do some things really, really well, and they do some things not so well. So the things they handle really well are general information, things like public domain knowledge, historical data, factual information, things like that that can be verified with multiple sources. Creativity and the arts, they excel at, again, that generation of new content based on existing or existing training data, they're good at, as we've kind of seen with a lot of the image generation, content generation going on. And then, as most computers typically are, good with human assistant and task delegation. As long as you kind of give them parameters and boundaries that are reasonably specific, they do pretty well as human assistants, right? But they have some issues as well. They lack the most recent data. So LLMs, even the most recent one, I think is only trained up until 2023 data. So they're missing like the last year or so worth of information. So you think about all the latest celebrity news over the last year, global news. You think about geopolitical things, financials and exchange rates. All of that has changed a lot in the last year. And the LLM, it hasn't been trained on that information. It doesn't know about it. You don't quite always get natural language. It does pretty well, but things like language complexities, cultural things, sarcasm, emotion, it doesn't usually end up quite perfect on that, at least not yet. There also really aren't sources. You can kind of get around this a little bit in certain ways, and we'll talk a little bit more about that here shortly, but traditional LLMs don't really provide source information of how they're getting that answer or where they found that data that they're providing and as the answer. This is kind of where you end up with hallucinations. If it doesn't know the answer to something or doesn't have something concrete to provide, it kind of makes stuff up. That's that whole, it generates something new based on something similar. Well, if it doesn't have anything similar or anything to go off of, it's going to generate something new out of the blue. And it does that, and it does it pretty convincingly. But this causes hallucinations. You can control a little bit of that with temperature by turning it up or turning it down. I want it more factual, more less creative, or I want something more creative. Things, if you're building social ads and content, you would want it more creative. Or if you're providing advice or financial data or facts or something like that, you wouldn't want it to be creative in that. And then there's issues like intellectual property, bias, and data privacy, all of which are massive topics that humans need to have a lot of input to determine which way we want LLMs to go. These are things LLMs do not currently handle very well, and things that we need to provide solutions for eventually. So we've already found out over the last couple of years that simply adding an LLM doesn't work. You can't just tack an AI onto something and expect good results, as we've seen from a lot of news articles over the last couple of years, right? You get into a lot of hot water if you're not careful. There are a few different strategies to help improve this. You can roll your own custom model. but that takes a lot of time, a lot of money, and a lot of skill. You probably need a whole team of data scientists, people with good domain knowledge and training capabilities and machine learning capabilities and so on, plus a lot of compute and just a resource space for the hardware and so on in order to train your own model. This is why you typically only see your big companies providing things like Microsoft and OpenAI that can provide these custom models. The next option down on the list, I kind of grouped these together, even though they're similar, but it's kind of different. Fine-tuning and few-shot learning. So fine-tuning is where you take a corpus of knowledge and you train the LLM kind of like an additional training. Think of like taking an extra course or grabbing an extra degree or something. So you kind of have an existing base of knowledge for the LLM, and then you're just tacking on this additional corpus of knowledge. But you would need, again, some resources to train that model to be very domain specific, to understand what they're doing. And you would need some compute and resource hardware as well to do that. So again, it still can be very expensive, especially depending on the data size. But for things like healthcare data sets and financial data sets that are very terminology heavy, very critical as far as answers and accuracy of answers, that might be the way to go. Few-shot learning is slightly less comprehensive in that you usually provide some examples and the LLM kind of trains on that and uses those examples to base its answers off of. So it's kind of providing a few extra learning examples for it to follow without doing a whole lot of actual training, but you're still needing to do that resource, time, money involvement there. The third option, which is where many companies and developers are going, is retrieval augmented generation, or RAG. We'll talk more about this over the next several slides, but this is where you provide some kind of external source of data to the LLM as just kind of a guide of here's relevant information, use this in your answer. Notice, though, that all three of these points listed involve training an LLM with specific data, just in various kind of sliding scales. So retrieval augmented generation, I mentioned, it's at the core just pulling from an external data source. This could be PDFs, it could be databases, it could be a website, it could be almost anything. And when I first came across this term, retrieval augmented generation, it looked really flowery and really complicated. But if you break it down word by word, it's really not as complicated as what it sounds. So retrieval is just data retrieved from some external source. Often that is a database, but not always. So again, could be documents or data store somewhere or website or something else. Augmented is you're going to augment the LLM's response with the facts that it retrieves from that external source. And then the part that the LLM is very good at is that generation piece. It's going to take that information that you're providing from the external source, and it's going to use that to generate its answer based on that. What we hope this gains us is some sort of explainable AI, or closer to explainable AI, right? How did the LLM get this answer? I can provide backing sources now of the data that was provided, the context that was given for the LLM to generate that new answer. And then I can help ground that LLM's answer with data that I know is high quality and relevant, right? So if I asked the LLM what an asset manager was, it may come back with an asset manager as a manager within a company, like a leadership or CEO or something. Where when you're talking about an asset manager in the financial industry, you're talking about somebody that is a stakeholder and owns stock and investments. So just asking the LLM, what does this person do, or how is this relevant? It may have a huge variety of answers to give. By providing information to it, saying, hey, here's some background information or some extra context, it can kind of guide it into the right topic area to provide that answer more reliably. So then how do you provide retrieval augmented generation to an LLM? How do you build that kind of system? How do you put it together? LLMs take media, not databases. You typically type out, ChatGPT, you just type out a message, right? You could provide it images as input, but you typically don't plug in databases, right? Or at least not yet. But it wouldn't know what to do with the database. Depending on the type of structured information you're providing it, it would have no idea what to do with that. So how do we relate database information from a variety of different formats or web pages or whatever else we have for our source? How do we make that relevant and readable to the LLM? The first piece of that is vectors. So we need to take data and convert it down to something the LLM understands. Now, again, we're going mathematical here, but don't worry, we'll kind of move out of that here in a second. So a vector in the mathematical space is a line in space, and it has a length and a direction. Now, this is great. This starts as the foundation, but me as a developer, I'm like, okay, how do we actually use this? What does a vector do in the real world? And here are a couple of examples I really like, because I can picture them really well and visualize it. The first one on the left is probably my favorite, which is you have an airplane flying through space or flying through the air, and you have a point. Maybe you want to go to lunch or something at a particular spot. So you have a trajectory. This says, go heading north. And you know how far you want to go, you know the speed of your airplane, you know about when you're going to get there. But let's say you have this external force, you have this wind now pushing you off course. It's coming from the northwest, depending on its speed and exact direction and stuff, it's going to push you off course. The further you go and the harder that wind, the more off course it's going to push you. So by calculating these numbers, you can start looking at, okay, I know I have this trajectory. I know this wind is pushing me this far, this fast. And now I can calculate the new vector or account for that old vector in order to put me back on the original trajectory that I wanted to end up at the location I wanted to eat lunch rather than way over here. With the Star Trek Discovery example, which is what's on the right-hand side here, it's somewhat similar. You're still dealing with kind of flight. But now, not only are you interested in the point in space where you're going to end up, the Discovery actually materializes in various parts of space. So not only do you care about the destination, you care about what's in the middle of it. Am I going to zoom through an asteroid belt or end up in the middle of a black hole along the way or get pulled in by a planet's gravitational pull? So now you're interested in not only the destination, but actually the path and the points along that trajectory to get there. Because you would need to calculate and go around those certain obstacles, right? To avoid hopefully disintegrating into space. What Google did, I believe back in 2012, was they built Word2Vec, which applied this concept of vectors to words. So they took words and the understanding and synonyms and everything, the way that we use individual words, and they calculated them down to a numerical representation. So for instance, we would have the vector representation for king. So you might think of throne, you might think of leadership, you might think of wealth, you might think of country leader or countries, and so on. And you could subtract the vector representation for man, add the vector representation for woman, and you would probably end up with the vector for queen. So now not only can we take concepts, we can start relating concepts. This is how our brains learn. We can take things that we know that exist and understand, and we can learn new concepts based on the things and similarities that we already have knowledge of. We can also compare things, not just to learn new concepts, but compare how similar things might be. So for instance, along similar vectors or similar lines, you could compare, okay, length to width proportions, shapes on the same vector are probably going to be more similar. But maybe you don't want to look at proportions. Maybe you want to look at size or surface area. Then all of a sudden you could start comparing across vectors and look at how similar are these two shapes? How different are they? Are these two things that I'm interested, are they totally different or are they really, really similar? This is where we come down to embeddings, because we need to convert that data into vectors in order to compare these, in order to calculate similarities, and so on. So now we can take data using a large language model to calculate vectors. We can take data and calculate it down to an embedding, which is a vector, a series of numbers. It could be hundreds or thousands of dimensions, and dimensions just calculate the variety of different features you want to include. So again, thinking back to that Star Trek Discovery, not only do you want to know the trajectory, but what are all the stops along that way that make up that path, right? So all the interesting things that you might have for a piece of audio or a video, now we can start comparing different types of data where we couldn't compare a video and a text document before. Now we can, because we're converting them down to a series of numbers that then we can compare all these things, various things that we couldn't do before. Okay, so we figured out we can take any piece of data, we can calculate it down to an embedding. That's something an LLM understands. Now, that's a lot of data. If we take all of our corpuses of knowledge, all of our data stores, data lakes, documents, unstructured data, web pages, and so on, that is a ton of data to have to sift through. I can't compare every vector. So the algorithm that's often used is KANN, which is K nearest neighbors or approximate nearest neighbors. And K just meaning could be 10 nearest neighbors or 30 nearest neighbors or 3,000 nearest neighbors or so on. The example that I really like to use is a library. So today you walk into a library or a bookstore, you typically have categories, nested categories of classification, right? You have nonfiction and fiction. Within that, you have genres, within that you have author, and then book title, and so on. But I might walk over, I know I like science fiction. I might walk over to the science fiction section, but I would have tens, hundreds, if I looked at the internet, thousands of options to choose from. And that's a really large search. How could I narrow that down? Well, now with vectors, instead of picking a generic large classification system like genre, maybe I would pick, I want to find books with a theme or plot based in Chicago. That's one key feature of that book, and I can narrow it down to a much smaller subset, which means that I get a much smaller retrieval and very short retrieval time because I can get exactly what I'm after based on those different features. And it could be any number of features, right? Depending on the dimensions of my embedding. So smaller search set is going to help give me smaller retrieval time, pull the relevant things related to my query. So we calculated our data down to a numeric representation. We've figured out how to search that very efficiently with vector retrieval, searching various features. The third thing that you can use to assist with LLM search is by providing additional context that you get by adding something outside of just the vector itself. And this is by using a graph. A graph is a natural representation of data. It includes the data itself, as well as additional relationships and connected entities and related info. So this stores the relationships alongside the entities, so you can easily see the network and the connections within your data. It helps you document the path of the data. It can help you answer why something is a certain way or what kind of fed into this point. You can provide alternate routes or alternate pathways or alternate recommendations. It can help you understand and find patterns in your data. So again, looking at a variety of different data points all together. I think this example is using Northwind data set. So products and purchases and customers and preferences and so on, all combined together. So this ends up with a web of connections and related information. It is nice that it also provides a good way to visualize the data and to explore it that way as well. But that is just a bonus. There's a lot of power just in the graph data itself. So then you can provide this additional context to the LLM. So for example, we're going to take a book domain, which is actually the demo I'm going to be doing here in a little bit, will be on this data set. So we have users who publish reviews that are written for books, and then authors write those books. So with this data set in a graph, I could easily answer, look for authors with reviews for multiple books. So I'd want to find an author that has a lot of reviews for several of their books, not just one publication. I might want to find similar users based on the reviews of the books and the related authors. So maybe I have a couple of users that really like certain authors and align really well based on, they like these authors and they despise these authors and so on. So I can easily answer these questions with a graph. So let's construct one really quickly. We have nodes and relationships are the two major components of a graph. If you're familiar with mathematical terms, these will be vertexes and edges. Nodes are going to represent your objects or your entities. You can label them, which means kind of categorize them or group them. If you're familiar with relational databases, you can kind of think of those labels as table names. So we have books and authors and reviews. You can also add metadata or properties. So for instance, we have a book title, we would have an author name or an average rating, we would have review text that gets written, etc. Then the relationships are what actually connects the entities. And it shows you there's a connection, but it also qualifies what type of relationship there is. It helps you understand what is the connection here. For instance, a book and an author. Well, there could be a lot of different things, a lot of different connections between a book and an author. But in this instance, the author wrote this book. Reviews are written for books. And you might have properties added to those. For instance, a review is written on a certain date or maybe updated at a certain date, or a review rating got changed or so on. So this is where when you combine graphs with your retrieval augmented generation, you can pull in that added context, all of that related information that you might have, the different types of entities, the different connections. You can pull this in and provide that to the LLM to say, here's other related info to the thing you're looking for. So it's going to provide the data as well as other context. Helps document the path, adding that connected context. You can also log interactions with the data itself. So I'll give an example here upcoming, and actually the screenshot there is from this too. You can also run network algorithms. So looking at influential entities or how things are connected, whether they're really connected or not so connected. You can also visualize data and see the interactions and pinpoint things that don't look right or that are unusual, and analyze the LLM's performance. Did it answer things well? Are there gaps that we can improve? You can see this really, really easily in a graph data structure. So this use case here is from our Agent Neo application, which I'll show on the next slide. But we have a graph data science library, and we have found that it is very hard for people to learn. It's kind of got a steep learning curve to it. There's a lot of things changing over time as algorithms and data science has adjusted and moved over the course of several years. And so we put in the graph data science documentation, some high quality blog posts and other good quality content, and we put that all into a knowledge graph, and then we put a chatbot over the top of it and had people ask it questions. Where do I find this? How do I do this? What's the syntax of this? And it would provide the answers. Not only would it provide the answers, but it would save the questions asked and the LLM's responses to the database. So then we can see what were the documents that were referenced, what was the answer it provided, what was the original question, what's the user conversation path look like? Are they getting the answers that they need? So the LLM was hallucinating answers on a lot of this. As I said, the graph data science library was changing a lot. So you wouldn't always have the LLM providing accurate, up-to-date syntax and responses. So this was a way for us to provide that updated info. We also included some extra high quality data and blog posts that we knew were good content. And this is a Streamlit and LangChain app that's running. And it logs the conversations alongside the data. And we can actually see over time, are the LLMs providing good answers? Are there dead points in the documentation that we can help improve and help people learn better? So maybe we need to update this page or that page, or hey, we have duplicate text across these different documentation points. We need to consolidate that and make that cleaner, and so on. So now we've seen we can take data, convert it down to a numeric representation. We can search it. We can provide extra context outside of that with a graph, and then we get our retrieval augmented generation system. So this is what the architecture looks like for RAG. You have a user providing a prompt of some sort, whether that's a question or some sort of input or something. And the LLM is going to generate an embedding for that, a vector representation of that question. It's going to go to the database and look for something, or whatever data store you happen to have, and look for something similar, the relevant information that's close to that. I'm going to pull that data back. It's going to grab the original prompt and that data and push it back to the LLM. And then the LLM is going to use that to generate a response to provide back to the user. There is this idea and concept of agentic workflows or agents or tools that's now being talked about, relatively new this year, I think. But it's very, very similar to the last slide that I just showed. The only difference is that the LLM is going to have a decision-making point of which tool or which data store to go out and access. It could be a service somewhere, it could be an application, could be a website, could be a database, and you're going to have that list of tools set up. And when the question comes in, the LLM is going to go, okay, based on this question that I have, which system do I route this to? Do I go to HR or payroll, IT support documentation? Do I hit the website or something else? So the LLM is going to have that determination step in there, but everything else is actually the same there. It's going to hit that tool for the source information, going to pull the relevant data back, send that back to the LLM. The LLM is going to generate a response and send that back to the user. Now, again, caveat, nothing's a complete silver bullet. The LLM still has some things that it's going to do really strange and can't necessarily qualify that. But there are things that have really improved. I will say I have noticed a huge improvement between OpenAI 3.5 and 4.0 just on the demo data set that I'm running right now. The responses are way more consistent and way higher quality than what they were on 3.5. You will have to do still a little bit of prompt engineering. Now, I know there's debates and stuff going on about how good that is and all that, but I can tell you that there are a couple of different things when you write prompts to ask it this way or that way will definitely impact the responses and the quality that you get there. And then you still might run up against context window limits. So depending on the LLM that you're using, the number of dimensions it can handle means how big that fire hose can be of the data you're sending to it. So if you're trying to send, a whole table's worth or, a massive subgraph worth, it probably can't handle that information. So you're going to need to kind of scale it down and provide only the most relevant results to that. So keep that in mind as well. All right, we are going to code and write something fun. So we have that book domain data set that we were talking about. We're going to ask, what I did is I took the review text for that. So reviews, and people write text, their review for the book. I took that text, I sent it over and had it create an embedding of that text and then save it to the database. And then what I want to do is I want to have somebody search for a book theme or thing that they like about a certain book. Let's say, for instance, dragons. I like books with dragons in them. So you could search for that, and then it would go out, retrieve the reviews that have something similar to that, and then pull back the related books from the graph and bring book recommendations back for you. So we are going to do that. And I'm going to build tonight using Spring. Now, Neo4j, we're going to use Neo4j graph database as the backend. Neo4j supports a lot of different frameworks. So, Quarkus, Spring, something else entirely, it doesn't matter. And Spring AI is their AI module for this, their project, and it supports a lot of different models and a lot of different vector stores or databases on the back end too. So there's lots of options here. Don't feel like you're hardwired into my preferences tonight, but we'll stick with this for tonight. So Maven and Java, sorry, Kotlin folks, and then traditional or stable version of Spring Boot. And I'm just going to kind of categorize this a little bit, and we're going to call this CJUG demo. And we'll stick with kind of the plain Jane stuff there. Then we're going to add a few dependencies. So we're going to create a REST API tonight so that I can query it and retrieve stuff back. And then we're going to use Neo4j in a couple of different ways. So I'm going to use the Spring Data project. Neo4j is one implementation of that. That's going to provide some nice database connectivity things and features. And then I'm also going to use the Neo4j as a vector database. So I'm going to use Spring AI's capability with Neo4j there. Then the last thing I want is my model. So I'm going to choose OpenAI tonight. But again, Spring AI supports a lot of them. So there's lots of options there if you don't like those preferences. We're going to go and download that project. Okay. Unzip it. So. Hopefully that's visible to everybody. Yes.
Yes, we're actually using graph database. Is it in the cloud or is it on your laptop?
So I have a local instance running right now, but I've done cloud. I mean, I do this demo sometimes on the cloud. It just depends. But to take the added latency, because I'm calling a public model, a web-based model, to take the public latency out of the database call as well, I'm running just a local database instance of this. So, and I can talk more about kind of the Neo4j deployment options or what exists out there too later if somebody's curious. But okay, so I always like to check the POM just to make sure everything that I asked it to pull in actually pulled in. So Java 17 and Spring AI is not currently on GA release. It's still sitting in a milestone release. So we are eagerly awaiting the 1.0.0 production ready version, but it's not here yet, just so you're aware. Okay, so we have the Spring Data Neo4j here. We've got the web dependency. We have the vector store for Spring AI as Neo4j there. And then we have OpenAI as our model of choice for now. And then everything else looks fine. Okay, so we're going to start off. Now, normally I would plug in my database credentials, but I have actually set those in the environment variables. So they're outside of the application, so I don't have to show username, password, and all that good stuff. But I also have the OpenAI API key that's there as well, which we're going to plug in right here. The first thing I'm going to need is I'm going to need a couple of beans. This is kind of like a packaged instance that I can access across the application. So kind of provide some things that I can access across the app. All right, so first thing we're going to use is the embedding model. So we're going to use OpenAI's. So return OpenAI embedding model. Whoops. It tries to be very clever, and it does pretty well for the most part, but it misses some things. So IntelliJ's latest update has a lot more like Copilot capabilities, and sometimes I hit the wrong key and it totally ignores what I'm saying. So, all right, we're going to see how this goes. So we have a system. Yep, did pretty well there, but it never gets this property right. It's actually Spring AI OpenAI API key. I don't know who named that property, but it's a long one. Okay, so that's our embedding model. That'll allow us to read the embeddings and also take our input query and embed it, run it against OpenAI's embedding model as well to compare in the database. And then we need to put together our vector store here. So it tried. There we go. Vector store. Okay, that's pretty good. But we need a driver, in this case, the Neo4j driver. And then we need to provide the embedding model here as well. And then return new vector store. Yeah, that's right. Okay. And then we need the driver and the embedding model. And then a config. Okay. Now, normally you could use defaults, but Spring AI is expecting a entity type of document. And we already know from our data set, we don't have a document entity anywhere with books and we have reviews. In our case, we took review text, right, to create the embeddings. So we need to customize this bean a little bit. So we need to tell it we're looking for a label in the database of review to search. And then we need to look for a specified index name because it'll create an index for documents as well. So we need to have it look for an already existing vector index. Now, if for some reason that vector index does not exist, I'm going to go ahead and have it initialize the schema to true, which means that my application could go ahead and create that vector index. I wouldn't normally do that in production because normally I like to use my database source of truth and let my application just read from that. But I'm kind of going around that rule just in case for tonight for demo purposes. Okay. So with that in mind, now we are ready to put together our domain. So I'm going to use records just for kind of conciseness here. So we're going to have an ID. And then we have a string, can't type, book ID, string title, and we have an ISBN, and then a ISBN, ISBN 13. It's an odd angle, so I'll blame it on that. And then we're going to do another record for review, and we've got our ID of string ID, and then string text, which was the text that I created the embedding for. And then we also have an integer rating for this, for the review. Okay, now we haven't done anything. We haven't connected these two entities, so we're going to do that really quickly. So we're going to add a relationship. And remember, our review is written for a book. So we have a relationship type of written for. And I always forget this piece. The direction has to be incoming because remember, a review is written for a book, which means that relationship is incoming to the book entity. So I have to specify that. And then we're going to have a list of reviews and we're going to call it review list or reviews. Okay, fine. See there, it didn't take the suggestion that popped up. But if there's a difference between hitting tab key and enter key, or depending on what the suggestion you're taking. So, okay, next thing we want to do is we want to create a repository class. This is going to let us access the database, so run queries and stuff against the database. So we have a book repository, and it tries. It did pretty well here, but we want a Neo4j repository, book entity, and the ID type is a string. Okay, clean that up. All right, now I had mentioned that we would need the review text is what's been embedded. So it goes out and does a similarity search on the reviews. And that's great. By providing those back to the user, great. I found reviews that have dragons in them. That doesn't really tell me a whole lot. I know those are reviews with dragons in them, but what are the books that are related to that? I don't have any book recommendations. So what we're going to end up doing is going back out to the database and pulling the related books. So we need a query in order to do that. So we're going to take the provided review IDs that are coming back from the similarity search. We're going to pass those into this query. So we're looking for books. With a relationship of written for and reviews on the other side of that relationship. And then we need where the R IDs, the review IDs, are in the review ID list that we're going to provide. And then we're going to return the book and the related connected entities here. So we're just collecting those into lists. And review, yeah, okay. And then we need to return a list of books. Oh, it suggested something and then it went away. We're going to call this find books. And we're going to pass it in a list, yeah, string review IDs. Perfect. So there, got There did really well. All right, last but not least, we need to provide a controller. So this is going to be our endpoints in order to access the application. So we need a REST controller. We need to inject a couple of things. So we do need to inject a book repository. We also need to inject a chat client. So this is so that we can basically chat with the LLM, the OpenAI. And then the last thing we need is our Neo4j vector store. Oh, not the repository. Vector store. There we go. And we'll call it vector store. It's just bugs me. Clean up. Okay. And then we need a constructor with all three of those things. So that's what it was bugging me about. And I'm actually just going to build an instance of this. Oops. It's not what I wanted. We tried. There it goes. Okay, much happier. Okay, now we need an endpoint in order to access this. So we're going to call this /RAG. And then we are going to retrieve a string. Call this RAG. We're going to send a request parameter. So again, we want to search the database for things that we might like in books. So we're going to pass in a search phrase. And then the first thing we need to do is that vector similarity search. So I mentioned that Spring AI expects documents as the entity type. So it's going to provide from that vector similarity search, it's going to provide documents back. So we'll have to convert that here in a second. It's kind of a pain, but okay. So we have our vector store, and then there's a similarity search method on that. We're going to provide the search request.query, and we're going to pass in that search phrase that's coming in from the user. That's going to give us our similar results. Now we'll have to go get the list of books, right, that are related to those reviews. So we're going to call this book list. It gets close. Not to find all the find books. There we go. Okay, and this is where it gets a little hairy because we have to take the results, which are documents. We have to map those. Just the IDs though. So document, get ID, and then I want to put those into a list so that it makes it easier, or so that we can use that list of IDs to provide to the query. Sorry about that. Okay. Last but not least, now we have to put together the prompt that's going to go to the LLM to ask it that question and for it to provide a response. So I need a new prompt template. But I haven't provided a prompt, so, or at least the foundations for one. So I'm going to do that. Prompt. Whoops. It's hard. And because I know you all probably don't want to see me write a bunch of text, I have kind of the basis of a prompt, and I'll talk about it in a second. Here. There we go. Okay, you're a book expert. Providing recommendations from high quality book information in the context section. Please summarize books provided in the context. So the context is the data, the information coming from the database, the books, and then it provides the original search phrase that the user was looking for as well. That's what's going to get provided to the LLM. Now we need to pass in that prompt, but then we also need to put in the values for those variables. So we're going to do a map.of, and we're going to pass in the context, which is the book list. And then to make this easier to read, because what I do is I output this to console so that we can see the data that's actually getting sent. So we're going to stream and map, and we're going to get book to string. There we go. Oh, it had it for me. Like collectors join does that too. Joining. There we go. And then I'm going to put each one onto a new line so that it's just easier to read in the console. It's a little bit of a pain looking at it, but it's much easier to read when we output it. And then we want the search phrase in there as well. Okay, that looks good. And then last but not least, I output this to console so that we can see it and actually verify the information that's getting sent over. And then same thing here, we're going to do template dot render. There we go. Okay. And then last but not least, we actually have to call the LLM. So we're going to grab our client. Oh yeah, it is called chat client. Chat client dot prompt and call, and we're going to retrieve content. So there's a whole object that comes back from the LLM with lots of extra information and such. We really just care about the LLM's answer, so we're pulling that content piece out of that object. And then I need to pass in the template to the prompt. template.create a message. So create a message to the LLM, and then it's going to actually call the LLM with that message. So if I have done everything correctly, we should be ready to run this and see how it works. So we're going to get into, what did I call it? CJUG demo. And then I'm going to size this up so we can see it a little bit better. Okay. So far, so good. Hopefully Wi-Fi holds up on this too, because that's the other thing. It makes calls to OpenAI. Do this. Okay, so let's query our database. So I'm using HTTP instead of Perl. It's just a nice implementation of it. And then we have our port 8080, which is our application, and we have our /RAG endpoint we define. Now we need to pass in the search phrase. So I may have mentioned earlier, I don't know that I did, but we could look for things like happy endings, because those are fun, right? Who doesn't love a happy ending? And we'll see what we come back with. Yeah. Okay. So here are the summaries of the books provided in the context. Forever Burning has a happy ending, as noted in the reviewer. Third book, this is Paradise of Glass with a happy ending. Bridesmaid features a satisfying happy ending, and then happy ending. Okay, great. This looks good. Let's go back and look actually the database information that got pulled. So you can see we have that Forever Burning happy ending, Paradise of Glass, happy ending with Monkey Down, and Beautiful happy ending. Okay, that's great. But this could be done with a text search, right? Why did we need RAG to do this? So let's look at another example. Let's look for something like encouragement. Okay. I'm almost wrapped up. Pass it over to Dimitri here. Let's look at something for encouragement. So we get, what do we think of when we think of encouragement? Story that uplifts and motivates, transformation and hope, inspirational, thought-provoking, uplifting narrative, inspired and hope-filled. So let's see what the database information provided. So encouraging, inspirational, inspiring and hope-filled, and inspiring. So again, now you're looking at not just the actual terminology, but the similar results to this. What do we understand about this, the word encouragement? What's similar to that contextually? Not just synonyms, but how do we use this? Let's do something a little bit more off the wall and stretch this kind of synonym similarity thing a little bit. Let's look for something high tech. See if I can find books that are high tech or something related to it at least. Okay, so we get 3 back. Appreciated for its intelligence, described it as intelligent. Mixed reviews, let's see, progressive for its time. Some aspects of technology did not age well. And then significant questions about the impact of modern machinery technology on ancient pre-literate technologies. So let's look at the actual database. So Lens of the World, intelligent was the review. Again, could be high tech, not necessarily, but could be similar. For the Terminal Man, there's one review that says technology doesn't age well. Very progressive for the time. Now with advances, it almost seems funny. So again, may have been high tech at one point in time, but maybe not so much anymore. And then this last one, Thriller Mystery, raises serious and substantial questions about what we have lost as the technology of machinery overwhelms technology of pre-literate people. So that could be high tech too. Seems a little bit more dystopian kind of stuff being provided there. But again, similar results, and we can understand where it's getting this information, and we can see the results that are coming from that database. All right, let's do one more that's even more off the wall, just for fun. And then we'll call it a day. Let's see if it finds anything related to caffeine. Because I'm always on coffee theme. We'll see if it provides anything interesting. Okay. Whoa, this is quite in depth here. All right, so we have Scanner Darkly, dystopian tale, deep psychological insight. Okay, word drugs. Caffeine has been linked in several case studies for being a mild form of a drug, right? This one, yes, this is the one. So Brooklyn. Okay, this doesn't look anything related to caffeine, right? Why did it pull this? The comment C1. And initially I thought, oh, bad data, I need to go clean that out. But then I got to thinking, what's the caffeine molecule? And it's C8H10 something or other. So C8, yes, it's off a little bit, but it pulled similar results because that is somehow related. It's the caffeine molecule. So kind of interesting, kind of weird tangential thing there, but kind of fun. Then the unexpected daughter and this dog walker. Okay. These again don't look anything like it. Directing readers to a blog for a fuller review. Okay, that's weird. Mention a blog for more details. Okay, this is really strange. Let's go look. All right, so Scanner Darkly, drugs, Brooklyn, C1, so that's all accurate. The unexpected daughter, look what blog it pulled. So coffee blog. So that's where it got the caffeine. Because, I mean, most of us, I definitely drink a lot of coffee for my caffeine. And same thing here. So that's how it's relevant and related. Again, you have to go back to the database to view where is it getting this info? How is this relevant? But you can really see that come through when you actually look at the data. All right. So with that, we'll go back and wrap up with some slides here. Okay. All of the code that I wrote tonight, you can see that out in our code repository, plus some additional other things that I didn't get a chance to cover tonight, like just the vector similarity search rather than the addition of graph, and you can really compare and contrast those results, and some other things available in the repo too. And then we also have several Neo4j and LLM courses that are available. So things like vector indexes, importing unstructured data, building applications, writing Cypher, query languages, and so on. So they're all free, self-paced online courses. So check those out at the second bullet point there. And then last but not least, if you want to learn more about Spring AI, again, looking at the models and the vector databases that it supports, check out that last one. I've just linked the Neo4j page, but everything's available in that left-hand menu. And feel free to contact me with any questions. I will turn it over to Dimitri now for his. Thank you very much.